All right, so good afternoon. Let's start. First, I'm going to go over the topic we did last time. It was the power of a point. Okay, so how do you define the power of a point? Where the power of a point is the following. First, you get the circle and you get a point, right? Suppose the point is inside the circle, then you just make any chord, right? And then you intersect the circle at A and B. And the power of a point is defined to be PA times PB, right? So that's the, and then you can say, well, what happens if I pick a different chord? Like I get another one here, I get a PB and PC, and is the product of PB times PC the same as before? Oh, yes, because otherwise the definition will not be a good definition, right? So basically, I need to show that PA times PB equals PC times PD, and that can be proved by using the the similar triangles, right? You just connect the AB and CD, right? Connect the AD and the CB, right? And then the two triangles are similar triangles, and then you can do that, right? So that's easy. The proof is easy. So we can define the power of point. That's a PB times the PC, right? And and now this is for what happens if P is outside of the circle, where you do exactly the same thing. You just draw any straight line intersect then the circle at 2 points, and then suppose it B and C, and then you have a product of PB and PC, and that's defining the power point. And again, you have to prove the other product to be the same, right? Same thing. Okay, again, it's a similar triangle, and you can do this. So that is the main result we did last time. And then what happened if you have well, if you just look at the picture dynamically, right? So for one of the line PDE, I can just move up, rotate actually. So P is fixed. I just rotate that. And upper, 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 and interior, at some point, I get a tangent line, right? So if when you get a tangent line, then PD and PE are all the same as PA. So here's just another proof, right? So PB times PC is equal to PA squared, right? That is this. Or you can prove this directly. So this is the way you can prove directly by using the similar triangle. So I want to give everyone maybe half a minute. Let's see why this works, right? Okay. And finally, we have one example here, right? So how to figure out the x value? Where to get the x value? You work for the power of m, right? You have two ways to compute the power of m. One is the 2 times 8, the other one is x times x. So that you can get x squared equals 16 and x equals 4, right? And after you get x equals 4, and then you want to compute the power of p, right? The power of p. So from one side, it's a 3 times, it's a x times 3x, right? From the other side, it's a y times 2y. So if you know the x value, you know the y value. Does it make sense? Okay. So that's from last time. Are there any questions? Any question? Excellent. So today, let's see. I'm gonna first just work on some homework problem first. So let's do a homework number 8. Homework 8. Let's work. Say homework 8 here. All right. And question number 7. So you get the equilateral triangle, right? You get a triangle here, and then you have 3 circles. Maybe here's one, Here is the second one, right? Oh, my picture was not very good, so they're here. And maybe for this one should be a tangent to everyone here. All right, so you get the three tangent circle. Okay, all of them are congruent, and each of the circle has radius of 1. And then I want to figure out what is A, B. Okay, what is A, B? Well, for this one, it's just a direct computation, right? So you can have, I'm going to have the center here, center of the circle, right, going this way, and then draw the perpendicular line. So this should be so this one should be a rectangle, right? A rectangle. Okay. So here's one, here's one, here's one, here's one. So this size should be 2 here. Okay. So that's easy for the 2 here. Now I need to figure out another one. So let me call that D here and E here. So first of all, DE is equal to 2, is twice of the radians. Okay. Now let's do the other one. What happened for the D here? Then I'm going to connect the A to the center of the first circle. Let me call that a 1, right? And this is a triangle of 30 degree, right? This is a right triangle first of all, and this is a 30 degree. Why this is 30 degree? Because it's an equilateral triangle. The angle A is 60 degree, but then you have OA to be an angle bisector. So one side is just 30 degree. So we can get this one basically here. That's 1, that's a 30 degree, right? And then we know that this is spatial right triangle, right? This is 1, and this is supposed to be square root of 3, and this is supposed to be 2 here. So it's 1, 2, and root of 3. And therefore, so I get this is root of 3, and this is root of 3. So my answer will be 2 plus 2 times root of 3, right? So that's for the question number 7. And let's do another one, which is hard. Question number 8. Question number 8. Okay, number 8. Let's see. So let me read the question. So a circle O is tangent to all of the 4 sides of the rhombus A, B, C, D. Find the minimum ratio of the area of the A, B, C, D to the area of the circle. Okay, many of you can guess the answer, but we have to, we have to figure out the why. Okay, we have to figure out the why. So if you guess the answer, that's not very good, right? Even if it's fine. So let's say we have a rhombus first, okay, and then I have a circle which is tangent to all of the 4 sides. All right, so you can get that, and then I have the A, B, C, and D here. All right, so let's say this is O, okay, and I want to figure out the ratio of the A, B, C, D over the ratio over the area of the circle. So it's the area of the A, B, C, D divided by the area of the circle, right? I want to find the minimum value of that ratio. Okay, so here is how we can do this. First, I'm going to just look at the triangle of, so just look at the triangle of, just make things, just make a small part of the picture. So I'm going to go this way here. So this is O, this is A, and this is B. All right. And suppose this is A and this is B. Okay. And I need to figure out where this is actually the radius of the circle. So here's the radius of the circle here, right? This is let me call that A, B, C, D, maybe E here, right? Maybe E here. So I want to figure out what is the OE? What's the radius, right? This is the radius of that. Okay, well, in order to figure out the radius, I can do the following. Okay, so first of all, you have A here, B here, the square root of the A plus the B square, right? A square, B square, that's a Pythagoras theorem. So that's a B, AB, right? But now I'm going to compute the triangle of the ABO in 2 different ways. One way is that you have 1/2 OA times OB. And the other one is a 1/2 of the AB times the OE, right? 1/2 cancel with the 1/2, right? So the left hand side is the A squared plus the B squared, take a square root, and times OE. The right hand side is just A and B. So we got the radius of the circle, which is actually AB over the square root of A squared and the B squared. Does it make sense? Right? Very good. Now we are ready to get the ratio. So let's do the so let's do this. So the denominator, well, the denominator is pi r squared. So it's a pi r squared, but the r is just the AB over the square root of A squared plus the B squared, and take the square, right? So that's the denominator. That is pi r squared. What happened for the numerator? Well, for the numerator, it's just a 4 times of the 4 times of the triangle of the ABO because of the symmetry here, right? You just need to figure out the one of the right triangles. And so this guy is just 1/2 times AB. So what I get here is that the numerator is a 2AB, right? The denominator, what's the denominator? Okay, where denominator is the pi, I get the A squared B squared, right? Take a square that, and then denominator of the denominator. So we get the A squared plus the B squared. Okay, simplify. AB cancel with the fact of the A and B, right? So I can get the following 2 times, and then the square root, the square of the A and B, right? So I can put that on the top, A squared B squared, and then divide by the pi times the AB, right? So that's the expression here. That is the expression here. Everyone understand that? Everyone understand that? Okay. But later on, so we get this expression. But later on, so I'm going to use the inequality. So one of the inequality we're going to use is that. So let's see. One inequality is that A squared plus the B squared is always a 2AB. Well, why? This is very straightforward. This is just because you get A squared plus the B squared minus 2AB. And then that is just A minus B squared. So that's why A squared plus the B squared is always bigger than or equal to the twice of the AB. We're going to learn those kind of inequalities later on. Okay, so in this semester. So this is bigger than 2 times the 2AB over pi AB. And AB can be canceled out. So you get the 4 over pi. And that's the minimum value. Okay, that's the minimum value. And the minimum value can be achieved if I have an equal sign, if and only if A and B to be the same. Okay, where if A and B to be the same means the original rhombus it has to be a square, right? It has to be square. But anyway, so this is how we can get that for the homework. Okay, are there any questions? Any questions? Very good. Today, I'm going to give you the second version of the power of a point, right? So last time we learned the power of a point, right? Just to quickly remind you, right? So what's the power of a point? Basically, it says that it's just a PA times TB equals PC times the PD, right? Like that, right? And now I'm going to have a second version of that theorem. So let's see. So today I'm going to, let's see, the second version of the power of a point. Okay. So basically, I'm going to prove the following. So let's say a circle here, right? So if we have a circle here, this is a center and this is a P here. Basically, it says that, okay, the power of the point, so the power of the point P, I can write that to be R square, R is the radians, minus the OP square. So that's the second formula. So it's just where, how do you define the power of the point? The power of the point is the square of the circle, okay, the square of the radians of the circle minus the square of OP, okay, minus square of OP. Well, why? So let's think of that. The why, how you can prove this? Okay, I'll give everyone a minute. Try to prove that. It's not hard. It's just a couple of nines, maybe two nines, and that's it. That's it. So it's very straightforward. So, so why the power of the point can also be written as R squared minus OP squared. Well, let's try. So anyone get that? Let's try that. So, where I'm gonna do this. Okay. So let's try to prove this. Proof. Okay. So let's start with R squared minus OP squared. Okay, R squared is R plus OP and R minus the OP. Right? It's a different squares formula. Okay. And now let's see what is the R plus OP. So I'm going to connect the OP, right? I'm going to connect the OP, right? And then just make an extension so that I can hit the circle at A and B. Everything's okay? I'm going to connect the OP and make an extension to both sides so that I have intersection, right? Two intersection points, A and B, with the circle. Okay. Now, can you tell me what is the R plus OP? Well, this is R here. R is the radians, right? So R plus OP is what? R plus OP is just a PN. Can you see that? OP plus R is just a PN. Okay. What is the other one? R minus OP. Well, I'm going to use R in a different way. So R, this is also my R here. R is a radians, so it's OP. So what is R minus OP? R is OB, right? It's a radius, but R minus OP just means it's a PB. And that's just my definition for the PowerPoint, right? So this is the power of the point of P. And then we are done. Does it make sense? Right? So this is very straightforward, right? So we have two different ways to say the power of OP. One is using the product. The other one is just use the difference of squares. Is R squared minus OP squared, right? R squared minus OP squared. So yeah, I think so. Okay. All right. So that's for this question. Now, what happened? So for the second version here, if the P is inside the circle, but then you may ask me, well, what happened if P is outside of the circle? Okay, so we have another theorem which is similar. Okay, so let's see. Suppose I have a circle here, right? And let's make it bigger. All right, suppose I have a circle. All right, and then I have a P outside. Okay, so P is outside, and then I got the P O here, right? So in this case, if P is outside, then the power of P, where I still want to write R squared minus OP squared, but in this case, OP is bigger, right? So, okay, so let's switch that. OP squared minus R squared. Can you see the difference between the two? The previous one is R squared minus OP squared because in the previous one here, R is bigger than OP just because P is inside, right? If P is inside, R is bigger than OP. But for the other one here, R is smaller than OP because P is outside, right? P is outside. And that makes sense. So if it's outside, if OP is bigger. So anyway, it's just the square of the bigger number minus the square of the smaller number. It's always like that. So it's a uniform definition for the power of point. So you have the OP square, you have the R square. It's a bigger square minus smaller square. Okay, and why? So can you prove it? And it's in a similar way. It's in a similar way. Is exactly the same proof. Okay, I'll give everyone 30 seconds. Can you write down the exact proof? Okay, so let's prove that. So first, I'm going to see the OP squared minus R squared. So this is equal to OP plus R and then OP minus R. Okay, so what is OP plus R? Well, again, I'm going to connect the OP and make an extension. All right, so suppose this is the intersection A point and the B point, right? You're going to connect the OP and make an extension. So you get two intersection points with a circle. All right, so what's the OP plus R? Where this is R here. So OP plus this R just means this is the PB, right? This is PB. All right, what is OP minus R? Where R is also here. This is also my R. So OP minus R is just a PA, and then we are done because that's just the original definition of the power of a point, right? So we are done for this. Does it make sense? Right? The two proofs are just quite similar, right? They're just the same. Basically, they are the same, right? Same proof. Okay. And I can give you a second proof. Okay, if you want, I can give you a second proof. So let's see. Here is the first proof. Okay, let's give you a second proof. Okay, proof two. Proof two. Let me draw the picture again. Suppose you get a P here, right, and a circle. All right, and for the proof two, I can do the following. I can just draw a tangent line. Okay, I draw a tangent line. So let me draw a tangent line. Let's see, it's hard to do it. Let's see. Okay, so I'm gonna do this way. First, I connect the OP, and I draw the tangent line. So maybe somewhere here. So this is a tangent line, and then connect this. All right, so suppose this is tangent, let me call T for tangent line. All right, so you draw a tangent line from P to the circle, right? And then connect this, and that can give you a right triangle. Does it make sense? So draw a tangent line, okay, the tangent line of PD. All right, so that's a tangent line, PT. And then connect all of the numbers, all of the points. Connect connect So you're going to connect the OP and connect the OT. So I know that the triangle of OTP is a right triangle, right? So this is a right triangle. Okay. Well, if it's a right triangle, now tell me what is the OP square minus R square. So what is the OP square? OP square minus the R square. What is this? Minus R square. What's the OP square minus R square? Can you tell me? Where OP is here, R is here. So by the Pythagoras theorem, that is just a PT square, right? And the PT square is just a definition of the power point. So this is the definition. So this is equal to the power of the point P, right? We did that last time. So let's see. If you forget, let's do. We go to outside the point. I think somewhere here. Can you see that? So this is the square here, right? So the power point can be written as a square of the tangent line segment, right? The square of the PN, right? So that's a definition of the power of the point. Okay, so we get that. And then we are done, right? So you have another way to prove it. Just give everyone some time. Everybody's good? All right, so I'm gonna give you let's try some example. Okay, the example so should be we should be using the power of the power of the point. Okay, the power of the point. So let's see. Let's do this. So here's some example. Okay, I'm gonna draw the picture. It's the picture is not easy to draw, so let's try that. Try my best. Get a circle. Okay, and then you have let's see, basically something like that. All right, so you start with the circle, all right? And then you have the following, so A, and then B, and then C, D, and P. Okay, so I'm gonna get the number there, 10, this is 8, this is 7. Okay, and angle P, so given the following, so BP is equal to BP is equal to 8, and then AB is equal to 10, CD is equal to 7, and the angle P is equal to 60 degrees. All right, suppose this, and now I want to find the radius of the circle. The radius of the circle. Okay, this is a little bit hard, so let's think of that for 1 minute. It's a hard question. But you can use the power of the point, okay? Power of the point. So where power of the point is just one step. After that, you still have to work for some steps, a few other steps after that. Okay, but the first step is the power of the point. So let's think of that for a minute. So let me ask you the first thing. So let's say, first of all, I want to figure out what is the PC, right? Step one. So figure out what is the PC. That should be easy. Okay, it's a PowerPoint, right? You pick up the P here. You figure out the PowerPoint P in two different ways, right? So that's good. So first of all, I know that the PB times the PA equals the power of the point P. But I can also write that to be PC times the PC plus 7, right? And then set up the equation, right? Get the equation and you can solve this. Everything's good, right? Good. So let's try to do that. So the left hand side, PB is 8, and then you get 18. Let me use the X for the PX for the PC. So X here, that's the X here. So I get X squared plus 7X. Okay. So it's a X squared plus 7X minus. So 8 times 8 is 64. It's 144. Okay. So 7X minus 144. And anywhere to. So how to simplify that? How to factor this? I want to do the factoring, right? Plus something, X minus something. Okay. How about the 9 here and 16 there? Does that work? So 16 minus 9 is equal to 7, right? And 16 times 9 is 144, and it's negative. Very good. So that means X value is a positive. X value should be 9. Very good. So I get my first one here. I get a 9 here. All right. But it's not done yet. There are a few more steps. Okay, what's the next one? So give everyone 1 more minute. So we have the first step. Right, first step first. We get that. And then we have, so this guy is a 60 degrees. Okay, we have to use this. So the next step I want to do is that I want to figure out, so step 2, I want to figure out what is AC. Okay, what is AC? Well, just draw the picture. So we have this picture here, right? So we get here, here, and here, right? So well, my picture was not there. All right, so let's see. You have A, C, and P. This is 60 degrees. This is 9. What is the other one? The other one is 18 because the 10 plus 8. Now, did you get what kind of triangle it is for the triangle of ACP? One side is 9, the other side is 18. So one is a half of the other one. And the one of the angle between them, is 60 degrees. Are you familiar with this angle? What kind of spatial angle it is? You see that? So you have 60 degree, right? And you have one side is half of the longest side. And so this is just a 30, 60, 90 right triangle, right? For the 30, right? 60, 90 right triangle. This is 1, this is 2, and this is root of 3. So this is exactly, so I can get that this is 30, 60, and 90 right triangle. Okay, 30, 60, 90 right triangle. And therefore, I can get my AC is the CP times root of the 3. So I can get the 9 times root of 3. So I can get this one here. All right, does it make sense? So that's my second step here. Okay, not done yet because I still have to figure out the radius of the circle. Now let's talk about the circle. So let's draw a different picture where it's a part of the picture. It's still the same picture, but it's just a different part of that picture. All right, so I'm going to get that one here. And then I got the following. So here is what we get here, right? This is A, this is C, and this is D here, right? So here we get the 9 square root of 3, and here it's 7, and this is a right triangle. Don't forget that. This is a right triangle, right? Why? Just because this side is right, so this is a right triangle, 30, 60, 90 right triangle. So if this angle is 90 degree, then the complementary angle is also 90 degree, right? Okay, now, so based on this picture, how do you find the radius of that circle? So that is a step 3. Okay, give everyone another 1 minute. It's a hard one. It's a hard question. So let's think of that. Someone in the chat made a good suggestion. So someone said that you connect the AD and then divide AD by 2. Okay, why? Why you can do this? Okay, so let me just work here. You connect. It says that you connect the AD, and so you say that connect the AD, and then you use the AD divide by 2. But I want to see why. Okay, I want to see why. Okay, so everyone think of that. Why you can do it this way? Well, this is because some time ago we say that if you have a diameter, right? If we start with the diameter, then suppose AD the diameter, then any other point from a circle, and then you form a triangle. That triangle must be 90 degree, right? That must be a right triangle. And then this is just the opposite of that. So it is still true, right? Because if angle C is 90 degree, then the circle of the AD is just 180. So that's just half of the circle. And therefore AD is a diameter. So let me write down the argument a little bit. Okay, so let's see. Give me a second. All right, so why the argument works? Just because you have your AD, right, is is twice of, or you can say 1/2 of the AD is the angle of the ACD, right? So that's equal to 90 degrees, and therefore the measure of the AD is 180. So this is just half of the circle, right? So if AD is half the circle, this implies that AD is is the diameter, right? AD is the diameter. So that's why the ratio, the radius is half of the AD, right? And after that, everything will be fine. Okay, so I'm going to finish this. Let's try to finish that. So how do I figure out the AD? AD is just AC square plus the CD square by the Pythagoras theorem. So we can get the square of the 9, root of the 3, take the square of 7. Okay, and where it's just the 1/2 81 times 3, and then we get the 49. Okay. Um, well, it's just a little bit tedious, but let's do it. So this is the 3 times 81 is 243, and 49, that's a 292. 292 here, right? 292. And you can write this one half outside. You can put that inside to become a quarter of this. So it's a square root of 73. Okay, and that's my answer. So this is my answer here, right? So that's my answer here. So the square root of 73, and that's the answer. Okay, this is very hard. So let me go back and give everyone 1 minute for the entire problem. So you have three big steps, right? Three steps. First step, power of the point. Okay, second step, the 30, 60, 90 right triangle. Okay, and the third step is the argument from the circle, right? How do you identify the diameter, right? Look at the rate, you look at the right triangle, and then the hypotenuse is actually the diameter, right? So everything's good, very good. So let me well let me let's see. I'm gonna give you the next theorem. It's called the angle bisector theorem. So angle bisector angle bisector theorem. So let's see, what is the theorem? Okay, so the theorem is following. I can have a triangle and have an angle bisector. All right. So suppose I have a triangle of the ABC, and then I have an angle bisector of D. Okay, so given, let's say this is angle 1 and this is angle 2, right? Suppose angle 1 is the same as angle 2, it's angle bisector. Then we wanted to prove that AB over AC, okay, AB over AC is equal to the BD over CD, okay? So let's see why. Okay, give everyone a minute. This is just a preparation for my next problem. So this problem does not need the PowerPoint. It's just a usual, the regular geometry problem. So think of that. All right, so let's see how we can prove this. Let's see, I'm going to prove. Well, the proof is that, so let me let me draw a parallel line. I'm going to draw the parallel line to that with AD. Okay, so and then make extension, go to here. So suppose this is E. Okay, so what I want is the following. Okay, I want to draw CE parallel with AD. Okay, everyone understand that? You go from C and you draw a parallel line with AD, and intersecting the line of BA at E. Okay, intersecting the line of BA at E. Everything's good? Okay, so if that's the case, let me call that the angle 3, and this is angle 4. Okay, so I'm going to write down a few equations. Okay, I'm going to write down a few equations. The first one is that I want to write angle 3 is equal to angle 1. Okay, why? Why angle 3 and angle 1 are the same, are congruent? Well, just because of here, right? If I have this one, if I have the parallel lines, then angle 1 and angle 3 are corresponding angles, right? So we can get the corresponding angle theorem. Very good. And now I get angle 1 is equal to angle 2. This is given. This is my condition here, right? Just because of the angle bisector. And then I'm going to write angle 2 is equal to angle 4. Why? Why angle 2 and angle 4 are congruent? Why? Why they are congruent? Why they are congruent? Well, again, it's just because of the same reason, right? So it's just because they are just because they are the two lines are parallel lines, so they are alternate interior angles, right? Alternate interior angle theorem. All right. So for three of this, I can get the first one is angle 3, the last one is angle 4, right? So angle 3 is equal to angle 1, angle 1 is equal to angle 2, angle 2 is equal to angle 4, right? So that just means that I get angle 3 is equal to angle 4, and therefore this is isosceles triangle. So I will get the AC equals AE. Isosceles triangle theorem, right? If you get two angles to be the same, then their opposite sides are the same. Okay, so I'm going to write down here. So this side is actually the same as this side. Okay, now we are almost done. How to finish? Okay, let me try to finish it. Okay, so I'm going to have, let's say, AB over AC. That's my left-hand side, right? Can you see that? I start with AB over AC. Okay, where I can write the AC to be the AE. I can replace AC by AE. Okay, I can replace AC by AE, and then this is actually the same as a BD over DC. Okay, why? Just because this is the picture. So if I just give you the picture here, and you will see something like that, right? So this is a B, this is A, this is E here, and this is D, and this is C, right? So if you have the two parallel lines, then those line segments should have the should be a proportional, right? So AB over AE, right? That's equal to BD over DE, and then we are done, right? And then we are done. So let me give everyone one more minute. Okay, let me give everyone one more minute. And equivalently, there is an equivalent because for the next problem, I'm going to use the equivalent form. The equivalent form will be the following will be the BD over AB equals CD over AC. Why they are equivalent? Can you see that? They are actually equivalent. Why? Well, just look at that, right? So just look at the cross multiplication, right? In the original problem here, the product of this one equals the other one. And look at that, the product of this equals the other one. So it's the same thing, right? But that's the form we are going to use for our next problem. So this is a warming up, where not warming up, it's hard. It's a preparation for my next problem. Okay. So think of that. What is this? So you go to the base here, right? So this one, so basically this one says the following. If you have that, right, like A, B, C, D, right, you get the following. You get this one divided by this one, okay, equals this one divided by that one, right? I shouldn't maybe use a different counters. So if I use the same counter, people just saw they are the same. They are not the same. I just tell you the numerator and the denominator. The numerators on the base, the denominators on the other side. Okay. So one mark the ones means the numerator, mark the twice means the denominator. Okay. So that's the thing you need to know for my next problem. Okay. So I'm ready. Uh, just think of that. Everyone, just think of that, and I'll draw the picture for my next problem. Okay. This is hard. So you get the two circles intersecting with each other, and then you get the, let's see, I know it's hard to let's see. It's not easy to draw the picture. The picture is hard to draw it. All right, so let me do this way. So you have the two pictures. You have two circles, right, intersecting with each other. Okay, and let me call that intersection point A, and then this is B, and then this is D. This is you get the X here, Y here, and Z here. Okay, and this is angle one, and this is angle two. Okay, everyone get that? So given that angle one equals angle two, and you see that that's why I need the angle bisector theorem, right? You get angle one and angle two. So this is a straight line going this way. Okay, you get a triangle, right? XYZ is a triangle, and then you get the angle bisector. So immediately you have the angle bisector theorem. Okay. So let's see how we can do this. Well, I want to prove the following. I want to prove the AX is the same as the BZ. Okay, so let's try that. Okay, so let's try that. So first of all, applying the angle bisector theorem. Okay. So I'm going to let me just give you one suggestion, right, for the first step here. So let's see, prove it. Prove just because angle 1 is equal to angle 2, right, by the previous theorem. So by the angle bisector theorem, I can get the following. So we're just look at the picture here. So what is it? I'm going to use this form here. Okay, going from the baseline. Okay, going from the baseline. So I'm going to do the following. So going from the baseline, I'm going to have the xd over xy. Can you see that? So this is a 1, here's the 2 here, right? So just from one side, right? The one side, the two line segment from one side of the angle bisector, you put that in the ratio. And then from the other side, I'm going to have, so this one equals the dz, well, I'm going to put that in a different way here. So this is a zd and then zy. Okay, I want to start with z. So can you see that? Okay, just give everyone some time. Right? So you look at the one side of the angle bisector, you get a ratio, and then the other side of the angle bisector, you get the ratio again. Now I don't need that anymore. I don't need the previous picture anymore. Just work in the argument here. So let me just multiply by the same number. So I'm going to multiply by, from the left hand side, I'm going to multiply by, so multiply by, multiplying by xz. All right, so from left hand side, I got the xz here. All right, from the other side, I got the zx, where xz and zx are the same. Can you see that? So I just multiply both sides by xz. So one side I write xz, the other side I write zx. Well, why? Because then you can hear that the numerator becomes the point of the power of a point. So what is that? What is this? What's the numerator? So z xz times xd, where that's the power of the x with respect to the larger circle, right? When you talk about the power of point, you have to identify the circle, identify the point. The point is x, and the circle is a larger circle, right? So this is the power of x with respect to the larger circle. But anyway, I don't have enough space to write the larger circle. So I can have, this is the same as, by the power point theorem, I have two ways to represent the power of a point, right? One is you go from xz times xd, but the other one, you can go to the other line here. Can you see that? So here's one line I can go. Here's another line I can go, the power of a point. So the other line I can go, that gives me the xa times xy. You see that? But magically, xy cancel with the xy in the denominator. So this is gone, this is gone. So that gives me the xa. That's the left-hand side. I got the left-hand side. And then basically the same argument can give you the right-hand side. So let me repeat. Okay, let's go to the other side. The right-hand side. And dx and the time the zd times the zx. This is the power of the z, the power of the point z with respect to the smaller circle. Can you see that? So let me use a different color here. So I'm going to have, again, I'm going to use this line here, but then I'm talking about the other line here. So I'm talking about the point of Z and with a small circle. So point of the Z with a smaller circle. Okay, so I can write this to be, if I talk about the power of Z with a smaller circle, I have another way to write down the power of the point of Z. So that's a ZB times the ZY. Oh, magically, ZY cancel with the ZY. That is the ZB, and then I'm done. It's a very, very nice proof. Okay, but it's very hard because you have to be very familiar with the power of the point. Okay, I want to give everyone 1 more minute, and that would be done for today. So anyway, so just give everyone 1 minute. Right. So the technique is that you first give the you first have the equation from the angle bisector theorem. Right. That's the main part. So the main part is this. That's the main part. Right. The main part is here, the angle bisector theorem. So you have two sides here, right? And then you multiply the xz from both sides so that the numerator becomes the product, right? The numerator of both sides become the product. But as we say that the product actually represents the power of a point. And the power of a point, you can have different ways to represent that, right? You change to another line here, and then there's some cancellation, right? And the same thing happened for the right-hand side. So this is very nice. Okay. All right, so I'm done for today. Everyone's good? Very good. So are there any questions? Are there any questions? Very good. So if there's no question, and that's all for today, and I'm going to see you next time, next week. Okay, bye everyone.
Thank you.
Mhm.
Thank you.